that contained all our information. Our V2 consisted of solutions only. Now V1 and V2 are clearly not orthogonal, and we want them to be. We want the vectors we look at to be orthogonal. We want them to be orthonormal. But what we can do is we can just force it to be. We can create our V2 perp so that this is 0. We just let them find what is V2 perp. We know what V2 is. It represents all the solutions only. We can find V2 perp. And V2 perp is just going to be written in terms of V1 and V2. It's not a complicated vector. And so along this axis, we have solutions. Along this axis, we do not have solutions, non-solutions. We start off with our initial vector. Now we apply our Grover operator. And what it accomplishes is that every time we apply our Grover operator, we're going to be rotating our vector so that it gets closer and closer and closer to the vector that represents the solutions only. So geometrically, it's very clear to see what's happening if you view it in this two-dimensional subspace. All right, so we went through all of this. We learned how to search. We learned how to search multiple lists. So now let's finally use this to solve our group theoretic question. So suppose, let me refresh your memory as to the question. So we have a finite subgroup of a group G. We have a subgroup of the automorphism group, which is also finite, and we're asking for the subgroup H. Is it equal to fixed S for S some proper subset of A? So we're looking to see if H are the points that are fixed element-wise by the set of automorphisms S. Right? H is the set of group elements fixed by S. And so this is how we accomplish it. So for each element in H, we're going to perform the following. We're going to search the elements of the automorphism group for those that fix that particular element. And so we may have one, we may have none, we may have a collection of them. It depends. It depends on the H. So for each H sub I, we're going to generate a set of elements. We call them L sub I. It may be empty, it may be not. It may not be. And then once we do this for each H, we use our list intersection algorithm to compute the intersection of those lists. So that's why we needed that LIA. And now here I didn't tell you how we searched, but you can clearly see that if we can search, we can use a Grover search for any of these parts of it. And so I didn't give you the details, but you just use Grover in a traditional way to search for the automorphisms that fix that particular group element. And then we use our LIA, and if the set S here, the intersection, is empty, then we output no. The answer to Q1 is no. Otherwise, we output yes, and we output the set. So just as Ventura, for the infinite case, was able to answer the question yes or no and give you the automorphisms that fix the subgroup, we're able to do the same. We had to have some restrictions because Grover only works when you're searching amongst finitely many objects. Okay, so here's the invariant version. So that was when we were fixing our elements point-wise. Well, what if we don't fix point-wise? What if we fix set-wise? So we want to know, is H invariant under the subgroup A? And so we view our subgroup and we view our subgroup of the automorphism group as lists of elements. Again, we're working with finite sets and finite subgroups, so we order them. And so we wish to determine if the subgroup H is invariant under the subgroup A. So we're saying, is alpha of H again in H for every H? And so what we do is, we have this giant superposition, again, our beautiful superposition, And what happens is we set up an operator in such a way that it implements all of the automorphisms of A. Here are alpha sub j. So whatever j is, our operator u is going to implement alpha sub j, that particular automorphism, on the group element. And now we run through all the group elements, we run through all the automorphisms, so we have this giant sum that has the group elements and all of their images under all of the automorphisms, giant sum. And so what's going to happen is some of the images are going to lie inside H again, and some of the images are going to lie outside of H. So in a very clever way, we set up our Grover operator so that it's going to flag or amplify the coefficients of the images that fall outside. So we'll be able to detect them. And so in this way, if we apply that Grover operator just a few times, like say 2 or 3 times only, we're able to see if we have images that fall outside the subgroup H. We can detect them immediately. So it's a really nice algorithm. And so if we have images outside, then we answer our question, no, it's not invariant. And if everything falls again inside of H, we just answer our question, yes, it is invariant. And again, I'm not giving you the details, but it's under the structure of this traditional Grover search. We just have to modify how we set up and modify a few things along the way. And again, if anyone's interested in details, I have it written up. So here's our last question. So do I have time for it?
Sure.
10 minutes? Okay. So our last question was this fixed point free question. So we have our group and we have our automorphism group. We want our group to be finite, and we want our automorphism group to be finite. And so we want to know if the automorphism group admits a fixed point free automorphism. And so now remember before we were fixing our group element and we were asking, does there exist an automorphism for which it's a fixed point, meaning that fixes it? Now instead of searching the automorphisms, we're considering each automorphism and we're working from there. So it's a different search. So we're saying for each automorphism, we're looking for the fixed points of it, not the other way around, like in the previous search procedure. So we're going to use this phase estimation algorithm to determine the number of fixed points from among the elements of H. If the number of fixed points is 0, we break our loop and we output yes. Because remember, we were just concerned, does there exist one fixed point free automorphism, yes or no? So if we find it somewhere along the way, we break out and we just say, yes, we found that there exists some fixed point free automorphism. If we somehow get through this whole thing, we may have the automorphism that's fixed point free. It may be the very last one. So we have to make sure we go through each and every one on our list. And so once we're done, if we've completed all of our loop iterations and we didn't break out of the loop, then we say no. Meaning we didn't find any of the automorphisms that have 0 fixed points. So the answer to our question will be no. And so this is just our general setup where we're considering them one at a time, look for the number of automorphisms. The one that has 0, we say, yes, this is it. It's fixed point free. But what about the details of it? How do I know how many fixed points it has? So remember I gave you that geometric view of the Grover search procedure. And so remember I told you that the Grover operator can be viewed